for the presentation. Okay, perfect. Thank you very much. No problem. Okay, so good morning, everybody. Who of you has had somebody in their family affected by cancer or amongst their friends? Look around. I could almost ask who not, and there would be very few ones. I'm a serial entrepreneur, and I had been working on completely different topics. I did a consumer tech startup called Shopkick that rewards you simply for walking into a store without having to buy anything, just by using your smartphone. Got the company sold, and I was thinking what to do next. And I made a decision to follow my heart and not my mind in terms of what I was going to do next. And that very quickly led me to the intersection of biology, engineering, and software, because I believe we will be impacted more on that intersection than in almost any other area for the entire humanity in the next 20 years. Now, when I live in the United States, I live in Silicon Valley. I've been in the US for almost 20 years. I was growing up in Germany, but I moved there. My little children were born there, and my wife is from California. So I was stumbling around the Stanford campus because I only live 4 miles away, trying to find the right people. I'm not a biologist. I'm an engineer from Karlsruhe. And I was looking for the right people. And then finally I met Sam Gambier, one of the world's most revered early cancer detection and treatment experts at Stanford University, ran an entire department in the clinic, radiology, and when famous people like Steve Jobs or John McCain had cancer, they came to him for help. Sam was on the advisory boards of Earli's, Google's life science arm, as well as Grail, the liquid biopsy firm, and he loved all the new technologies, but he was very worried about one key thing that nobody seemed to be addressing, sort of the elephant in the room. And that is, for the last 20 years, pharma companies have spent billions of dollars trying to find natural biomarkers on the outside of cancer cells to make them druggable targets. The problem with that approach is most cancers don't have natural biomarkers on the outside of cancer cells. And even those few that do, don't have them for all patients because of individual mutations. Because after all, what is cancer? Cancer is a mutation of your own cells, which means the biomarkers naturally also mutate. And that's why there is no single cancer drug that works for all people. And what do pharma companies do in response? The only natural, smart, logical way they could respond is they're taking populations of patients and they slice them into ever more narrow slices of submutation types. If you have this mutation, then this drug may work. And they're going to develop another drug for this submutation and that submutation. You know how much it costs to develop a drug? $2.5 billion on average. And it takes 12 to 15 years. And most of them fail in phase 3 trials at the very end of the process. That's the status of pharma today. Now you're wondering why it takes so long until a new drug is out? So is there a radically different way we could look at this problem? So I'm going to pitch you Earli, but I'm not pitching you Earli because it's my company. I'm pitching you Earli because I am believing that this approach that's behind it is but the spearhead of a completely new way of treating and thinking about how to treat cancer. And forgive me for being biased, otherwise I wouldn't be spending my time on it. But I believe it's truly a requirement that we think about this direction, and other companies, please come spring up and do something similar and go in the same direction. We need more of this because we require that we are completely reinventing how we think about cancer. So imagine if we could flip the whole problem around. Imagine if we could no longer look for natural biomarkers at all. What if instead What if instead we created a genetic construct that goes into the cancer, in fact, into the cancer cell nucleus, where the mutation happens that causes the disease? And what if we could create that sequence that flips on like a light switch when it's cancer, but not when it's not cancer? And if it does flip on, what if we could turn the cancer cell into a little factory and force the cancer to produce any protein we want? Any protein we want, which means for diagnostics, we would create a protein that is an epitope that binds to a radioactive contrast agent so we can see it in a PET scan. And for therapeutics, we would create a cytokine, which is a messenger to the immune system to start attacking the tumor and kill it. Let me rephrase. What if we could take control of the cancer? What if we could tell it what to do rather than us trying to catch up with the latest mutation and it constantly being at least a step behind, likely 2 or 3 steps in an endless cat and mouse game that never ends? Do you see what I'm saying? What if we could take control and engineer a solution rather than search and search and search for the next elusive biomarker? That's what we're trying to do here at Earli, okay? So let's dive in. I'm going to ask you a simple question. What is the holy grail of cancer? In one simple sentence. Very simple language. Kill the bad cells, but don't kill the good cells while you're doing it. That's what it is, right? Now, that simple statement belies how incredibly difficult this is. This is from the prologue of one of the most important books ever written on cancer treatment and history. 2011 won the Pulitzer Prize. And in the prologue it says, malignant and healthy growth, in other words, cancer and non-cancer, are so genetically intertwined, remember it's your own cells that mutate, that unbraiding the two, separating them, is one of the hardest scientific challenges faced by our species. And that's why nobody has done this before. It's very hard. So let's take a look at this lung here. These yellow things are lesions. They could be cancer or they could be completely harmless. On average, 94% of these things are completely harmless. 6% are malignant, and so malignant they will kill you if you don't take them out. Now, can you please tell me which one is malignant? Anyone? You're all correct by not responding. No one knows. Not even Sam Gambier, who tried to put his life work to this and lost his only child to cancer when his child was 16 years old to brain cancer. And he himself died 4 years ago from cancer, and his wife died 1 year ago from cancer. The family's gone. The entire family was wiped out by something similar to this problem. No one knows. So what can clinicians do? They have 2 choices. They can ask you to come back in 6-12 months for another scan to see if it has grown. If it has grown, it's cancer. Unfortunately, it was already cancer the first time you were there, just no one treated you. And in the meantime, the cancer hasn't just gotten bigger. It might have started spreading tiny, tiny micrometastases. They are so small you can't see them. They're smaller than the smallest yellow point you can see here, which means your primary tumor will be taken out. Everybody hopes you're going to be fine. It's called remission. 2 years later, your cancer is back. 50% of all people with lung cancer will get remission. Once you get remission, you're automatically a stage 4 cancer patient, and your chances of survival for the next 5 years go down from 60% to 8%. You have a 92% chance of dying in the next 5 years. The other option is to put a needle through your throat, into your lung, try to take some cells out, send them to pathology for evaluation. That costs $20,000 to $40,000 in the United States. It's usually done under full anesthesia to keep your lung from moving. 22% of people who undergo the procedure start coughing up blood from collapsed or bleeding lungs. 1% dies on the gurney from the procedure. And the worst part is if you have lung cancer, in 16 to 40% of all cases, they will not find it because the needle picked the wrong cells because it's so hard to navigate. You go home with no treatment. In fact, you get a negative statement, you are free of cancer, you're good. In fact, you have cancer and nobody treats you. That's the state of current treatment in the United States, in Europe, in developed countries around the world, not even talking about developing countries, where it's even worse. So what can we do about this? What would change if we could light up only the malignant nodules and not the benign ones? Those are those two. The next day you would be in surgery or in radiation, and you would be treated. All right, so liquid biopsies, which you might have heard of, really cool stuff. You get a blood sample taken and they tell you might have cancer. Really cool. They can tell you what it is, that it could be cancer, but not where it is, because it's a blood sample. Standard imaging might tell you where something is. You see that little thing up there in the lung, but not whether it's cancer or not. A lot of things look like cancer. They're totally harmless. You can't operate on every single thing. You only have 5 lobes in the lung. If you take them out, you can't breathe anymore. The last one is Earli. Earli is designed to tell you what it is and where it is. That's the new approach, right? And again, I want to state it again. I'm not here to just sell Earli. This is a new approach where you are forcing the cancer to help you. And we need more of that, not less. I want competition. So I'm inviting everybody to go in the same direction. All right, so this goes beyond screening and detection to diagnosis and treatment. And how important this is in the clinic, you can see here. This is Cyriac Roeding. He's one of the best people in the world for lung cancer treatment. He runs the Thoracic Center in New York at Sloan Kettering. And he says if we had a procedure that separates malignant from benign, it would change the game in the clinic because what we have is not good enough. That's the advisory board. And these are really, really smart people. I am amazed every day that we can work with them. The guy on the bottom right-hand corner is probably the scientist you should all be in awe of, because he developed immuno-oncology. He developed the idea how to turn your immune system against cancer, your own immune system. He got the Nobel Prize for it in 2018, Jim Allison. Upper left side, Bob Langer, MIT. We just saw an MIT presentation. This guy's the most cited engineer in history of humankind. He also helped start Moderna, the vaccine company. On the upper right-hand side is Phil Greenberg, who started Juno, an immuno-oncology firm sold for $9 billion. And then former ex-deputy commissioner of the FDA. So all of these people are here because what we do is different. You got the synthetic construct that doesn't activate in normal and benign cells, but in cancer, it turns on like a light switch and turns the cancer cell into a factory that makes the epitope that makes it visible in a PET scan. So in other words, we design programmable genetic constructs that turn on only in cancer and force them to reveal and ultimately kill themselves. That makes this the first synthetic target platform. Remember what I started the presentation with. I said pharma companies have spent billions of dollars trying to find natural biomarkers to make them druggable targets. Remember that? Unfortunately, there are very few of those. They're elusive, and they change from patient to patient. This is a platform that makes a synthetic target. We can take control of it. We engineer it. How does this work? There are 4 main things. The first one is a cargo container for genetic content. It's a nanoplasmid for the PhDs in the room. And inside the nanoplasmid, we're putting an if-then clause in. If it's cancer, then produce an output. The output is the reporter. The reporter is either the protein that helps us for diagnostics, for an image, or it's the cytokine that activates the immune system for therapeutics. And the last part is a non-viral delivery agent that gets it to the nucleus of the cancer cell. Now, that part is really hard if you don't want to go to the liver. Anybody in the room who's a PhD in biology? Ah, there you go. Okay, so have you ever seen a lipid nanoparticle that doesn't go to the liver? Yeah, no, exactly. We haven't either. So that was part of the risk when you started the company. It took us 4 years to develop something. By the way, you all know lipid nanoparticles. You just don't know it. They were in your body when you got the corona vaccine. But they all go either into your muscle tissue or into your liver. The liver in your body is there to flush out anything that doesn't belong there, including alcohol, but also lipid nanoparticles, which means that's where they go. To develop something that doesn't go there, actually goes to the lung, is really hard. So that was one part. The other part is this up here. The promoter is the heart of the whole system. Is it cancer or not? Remember the prologue of the book, how hard it is to differentiate malignant from benign? This is the problem. This took us 5 years. And in these 5 years, we completely hit a wall. In the first beginning, we used an endogenous natural promoter. A promoter is a genetic sequence, and it was really well differentiating between cancer cell lines and healthy tissues in the lab, where the cell lines never change. They're always the same. But then, Then you take individual cancer samples from patients, from real people, and you try to turn it on in each of these. Well, it turns out the mutations are all different. They don't turn on anymore. So next step, logical step, let's take a look at the driver mutations, the genetic mutations that cause the disease, right? We're going to look at each one of those. Unfortunately, in lung cancer alone, one cancer, it's over 100. If you look at each one, the construct gets so large, you can't get it into the nucleus anymore because it's tiny. So either you're accurate, but you can't get into the nucleus, or you're in the nucleus, but you're not accurate. Great situation for startup, isn't it? Well, your funding is running out. Well, that was early. 1.5 years into the company. So then we said, okay, 2.5 years ago, we said, okay, what if we thought about this completely differently, this problem? What if instead of looking at each driver mutations, what if we didn't look at a single one of them, none of them? What instead we looked at the downstream commonality effects of what these dysregulated, these messed up driver mutations are causing, the result. And that is, for example, rapid cell proliferation, lack of cell death, which are hallmarks of cancer. Then we used artificial intelligence and a lot of machine learning in order to look at 20,000 sequenced cancer samples, noodled it through with lots of algorithms. Then we created a wet lab process with thousands and thousands and thousands of mutations of how we are arranging these different things. And we came up with the master dysregulated transcription factors as the core element and promoter cores and enhancers to boost the signal. I'll spare you the details, but take a look at how this looks.
Earli's genetic vector is delivered into cancer cells by a non-viral agent. This sequence contains a synthetic promoter that binds the dysregulated transcription factors that are abundant in cancer cells, but not present in normal cells or in benign lesions. The promoter switches on inside the malignant cell and forces it to express an encoded protein.
And this is the output.
For therapeutics, that expressed protein either kills the cell or activates the immune system to destroy the cancer. For diagnostics, the expressed protein acts like a docking station for an injected radioactive tracer, which then makes only the malignant lesions visible in a PET scan, leading to immediate treatment.
Okay, so in other words, what we are doing is now a completely different approach. On the left side, you see what we first discovered when we used the Stanford construct, the original proof of concept. These are individual cancer patient samples, lung cancer samples taken straight from the operating room. We looked at ex vivo, in other words, in the lab, whether our construct would turn on in these samples. It only turned on at 13%. It worked really well on cell lines that never changed for 50 years. But if you look at individual cancer patients, breakdown. So then 5 years later, and a lot of rocky roads later, the same samples turn on in 98% of these completely synthetic promoters, very synthetic genetic constructs. Now, it's great if you know if it's cancer, but it's not sufficient. You also need to know when it's not cancer, and make sure you don't turn on in that case, because otherwise you have lots of false positives. So now the trick is not to compare only healthy tissue against cancer, because remember what the problem is in the clinic? Do you remember the picture with the lung? The problem is not healthy tissue. The problem is benign lesions that look like a cancer, but they're harmless. Getting these samples is hard because everybody throws away benign tissues. Oh, you don't have cancer. Trash. So we were going on a hunt to find benign samples in blue. You can see how healthy against cancer, against benign samples, they're not overlapping. And here you can see 9 different things that look like a lung tumor in an image, but they're completely harmless, especially granulomas. They look really like a tumor when they're tiny. No signal from those, but lots of signal from the cancer. Why is that? Because this is not normal anatomic imaging, this is genetic imaging. We're looking at genetic differences for the first time. And now you could say, well, the adjacent tissue that's normal is also producing a signal, but if you look at the next level, phosphorylation level, it's a 98% difference between the two. So you can very clearly identify it's cancer or not. Next step, we took it from 30-gram mice. You know, mice are sort of the workhorse, which is a little silly, but you use the mouse in order to find out whether something works or not, but actually the mouse is not a very great predictor. You got to go into large animals. So we went into 60-kilogram pigs, almost the weight of human beings, next, with a fully functioning immune system. On the left side, you see a pig that has no early activated, and this is the liver outlined in yellow. It has 5 liver tumors, only one of them is visible, and even that has a very low level of signal on the color scale. Now I'm going to show you a pig that has early activated, has 4 tumors in the liver. 1, 2, 3, and next to the big one, 4, all at the highest level of signal. How is this possible? It's because the cancer was turned into a factory. It had to make an epitope. It bound to the tracer, and now it accumulates the contrast agent. You can see it. So in other words, early is becoming the bridge between detection and treatment. Unless you have a clear diagnosis, there will be no treatment for you. No one treats you unless they can tell you it's cancer and see it in an image. So the next step for us is to take it to humans. In the next year or two, we're going to take it into the phase 1 and 2 human trial in order to understand whether it works in humans as well. And the goal is to get rid of this needle biopsy, which is costly and expensive and dangerous. That's a very large market, $50 billion globally for lung cancer diagnostics. In the US alone, it's $16 billion a year, and $20 billion for liver and all these other cancers that are coming next. All right, so now, last part I want to talk about briefly is therapeutics. Okay, so I got to hurry. Therapeutics, you can use the same platform for therapeutic opportunities by releasing out of the tumor a cytokine that activates the immune system against it. If you look at a drug like Keytruda, which is an amazing drug, it uses your immune system to stimulate it to kill the cancer. It's beautiful, but it only responds in 30% of all patients. 70% show no response. Why? Because your immune system doesn't even know there is a tumor or doesn't send enough immune cells to kill it. So now what if you could use the cancer itself to release a stimulant, a cytokine that activates the immune system to attack and kill the cancer, and then you give them Keytruda, not the other way around. And I'll show you briefly some data. We can release a cytokine straight into the tumor microenvironment. It stays for 3 days. Normally when you inject it, it's only 20 minutes to 2 hours, super toxic. You can't really do that. If it's slow, like a drip machine, it's much better. And you can increase the ratio of the cells that you need to kill the tumor. You can see what happens without treatment in a mouse, with Earli, with no payload, when it's just the construct, slightly toxic. But when you release the cytokine, look at how the tumor volume, the size of the tumor, goes to 0. And we've done that in multiple models. I'm going to skip here for the interest of time. This is probably the most important one because it's actually a human tumor in a mouse with a human immune system that's injected. And you can see how the tumor is shrinking. And that's because the immune cells are suddenly recruited to the tumor to attack it. That's what we need to do in order to address it. Lastly, we can make any protein, remember? We can use AI to make even better cytokines that nature doesn't even provide and have a better effect. So in essence, we've gone on a 6-year journey here, and hopefully we won't be the last one to do this. I hope that will be many others coming. Finally, the White House this week, 3 days ago, identified this approach as a new major direction in cancer and highlighted it, which was a big step because we believe the next era is to turn cancer against itself and no longer rely on us trying to search for elusive markers. Thank you.